So what we're going to do now is, we've already looked a little bit at collapsing bayes tests. We're going to focus on running SCAT, all right, which is a similarity based test. So recall that for collapsing bayes tests, they tend to do very well if the majority of variants within a region are causal, and all of the causal variants tend to have similar direction of effect. SCAT, as a similarity-based test, as with C-alpha and other popular tests in this category, do not require variance, tends to do well when fewer variants are causal, and in the situation where variants tend to have opposing directions of effect. That's to say, some variants increase disease risk and some variants decrease disease risk, for example. So to actually run SCAT, the first thing we need to do, clearly, is to type in library SCAT. And this loads the SCAT library, which is available from CRAN. So we highlight that, hit run, and didn't give me any errors. So that means that SCAT is now up and running and available for use. So the first thing we're going to do is we're going to look at the association between the variants inside of gene 1 and trait 1 and see if there's an association there. So we again read in the variance, so that's z equals as dot matrix, read dot table, force it into a matrix, and we're going to calculate the minor allele frequency and then also scan in the trait values. So we highlight these and hit run. Then again, it's read in 1,000 values. We're going to now find the variants that have allele frequency less than 3%. So we highlight line 174, hit run. And so now we're actually ready to run SCAT. So running SCAT basically requires two steps, always. The first one is you have to estimate the null model, which is to say the model in which the variants are not present. So in this case, we're going to store it inside of the variable obj. So obj equals scat underscore null underscore model. And so here, y.c twiddle1 is our null model. So it's our outcome, y.c. And when you say twiddle1, it just means that we're looking at the model in which it only depends on intercept. Then we specify that the outcome type is continuous. So we highlight line 176, and then we hit run. And having done that, we can take a look at what is inside of obj. And so it's basically not something that you would typically look at very much. There's a whole bunch of things that are basically just helpers and that are used within the SCAT package itself, that are used in the backend for SCAT. Then to actually run SCAT on a particular set of variants, in this case stored inside of the variable z, we do scat z, and then we give it the null model. $p-value just means that we're going to pluck off the p-value from the results. And so if we highlight 178 and run it, then what you end up with is a p-value of 0.185, which is the p-value for the association between the variants inside of this region and the outcome using SCAT. You get a warning message, which is that the genotypes of some variants are not the number of minor alleles. And so that's to say that these genotypes are flipped. And so that's something that we already observed previously. When we looked at the minor allele frequencies, we saw that there was one variant which was miscoded. It was a common variant, and since common variants get relatively low weight, we basically just chose to ignore it. But SCAT does a little bit of a check just to make sure that you know that there is something that may be miscoded. So line 178 is looking at all of the variants within the region and testing for their association with the outcome, and we're not able to call statistical significance at the nominal level, 0.05 level. So what line 180 is doing, it's now restricting attention to the rare variants, all right? And so a couple things to note. So here, instead of just z, it's z bracket comma RVS, which is restricting attention to the rare variants. But note that the null model remains the same. So regardless of the set of variants that you're looking at, the null model has not changed. And so that's one of the things that actually makes SCAT very, very powerful and very, very fast if you're running it genome-wide. This null model calculation only needs to be done one time. All right, as long as you're looking at the same trait and the same covariates and the same set of individuals, then it doesn't matter which set of variants goes into there. It doesn't change because the null model is the model without any variance. And so it doesn't matter which set of variants it is. None of them have any influence on the outcome because this is the null model. So that being said, with the same null model, we're using a slightly different modified set of variants, and we're going to run line 180. To test for their association with the phenotype. So we run this and we again get an unremarkable p-value of 0.11. Still nothing, nowhere near near significance. And so a couple of things that I wanted to say. Running scat is relatively straightforward. It's simply 2 lines of code. You do need to calculate the null model separately, and then you can just run the scat function. The other thing I wanted to note is that when we did binary collapsing, or did collapsing previously, we were able to call significance using the collapsing tests. And so this suggests that, at least among the rare variants, a fair number of them are truly associated with the outcome, which is why that approach tends to do a little bit better than scat, at least for this trait and this gene. On the other hand, now we're going to run scat, this time on gene 2 and trait 2. So we're going to again read in the variants inside of gene 2. So we hit run. Or line 188. Then we're going to calculate the minor allele frequency and scan in the trait values. That's lines 190 through 191. And we hit run. Again, you've read in 1,000 trait values. We're going to restrict attention to the variants that have allele frequency less than 3%. That's line 193. We hit run. And then we're going to calculate a null model. So because our outcome has changed, all right, then we need to run a new we need to get a new null model. So we hit this, and then we hit run. And then now we're going to test for association between all of the variants within this region and the outcome of interest. I should have mentioned earlier that by default, scat does use weights. The particular weights are a beta density function evaluated at the minor allele frequencies with parameters 1 and 25. That's the default there. So under these default settings, the common variants are included in the analysis, but given relatively low weights. So let's hit run with line 197. And you see a p-value of 0.005. So you'll recall that when we used collapsing-based tests, we were not able to get anything near statistically significant. But what this illustrates is, on the other hand, using scat, you are able to get something that at least at the nominal level would be called significant. And so what this illustrates is that there may be variants inside of this gene that have opposing directions of effect, or something else is going on. But regardless, it's a situation where collapsing does not do very well, but scat does much, much better. All right, now let's restrict attention to the rarer variants. That's line 199. We highlight that and hit run. And again, you end up with a p-value that's about the same, 0.0057. Okay. Either way, you're able to get something that is called significant at the nominal level, whereas by using the collapsing-based approaches, nothing would have been called significant, or this region would not have been called significant. What we're going to do now is we're going to look at the omnibus version of scat. So that's scat-O, where we first fix the row parameter. So recall that scat-O is taking a weighted combination of the collapsing-based test and also scat. And by doing a weighted combination, it may do well better in the omnibus. So there are certain situations where collapsing does better. And so an example of that is for trait 1 and gene 1. And then there are also settings where scat does better. So that's an example of that is with gene 2 and trait 2. Given that, the omnibus test scat-O is basically a combination of the two. But before we run into the optimal version of scat-O, where we search across a grid of different row values. So row is the weight that determines whether you're running scat or whether you're running collapsing or something in between. We're going to fix the row values. So the first thing we're going to do is we're going to fix the row value, in this case called r.core inside of the function, at 0. And so this should be then the same as running scat by itself. So if we highlight line 208 and hit run, you get a p-value again of 0.0057, which is the same thing as what we got above. So setting r.core equal to 0 corresponds exactly to scat. We're now going to highlight line 210 and run that. In this case, we set r.core equal to 1. And so if we run this, get a p-value of 0.7, which is not very, very not significant in this case. And this is basically the same thing as doing a weighted count-based collapsing. However, the weights that are used here are the beta 125 weights as a default. You can specify alternative weights, but as a default, it's the beta 125. If we set r.core to be 0.5, then this should be something that is between scat and collapsing. And in this case, if you run it, you get a p-value of 0.26, which is which happens to be in between. But it's neither scat nor collapsing. It's some combination of the two. So specifying the row value, if you have a good idea of what row value to specify a priori, is fantastic. However, in practice, you never really know the optimal value before running the analysis. So with that in mind, what we're going to do is we're going to run scat. Again, we feed in the same rare variance, the same null model, and now we say method is equal optimal. And so what this does is it now searches across a grid of different row values and calculates p-values, and then picks the minimum, and then adjusts for having done so. Or at least intuitively, that's what's going on. And so if we highlight line 220 and hit run, you get a p-value that is 0.011. So that's not as significant as if you had run scat by itself. But on the other hand, it's much, much better than if you had run collapsing. And so that's typically what happens, or oftentimes what happens when you use scat-o. You end up doing better than the lesser of the two options of scat and collapsing, but you do lose a little bit for having searched across a different range of values. By setting method equals to optimal.adj, so it's slightly adjusted, this gives slightly better type 1 error control in the tails and can be a little bit less conservative in some situations. So if we highlight line 222 and hit run, you see your p-value is 0.010. Very similar to before. So one thing to note across the analyses that we've been running recently is that we have not rerun the first step, which is calculating the null model. We haven't done that for a couple of the different exercises. It's all the way back up here. For all of the subsequent analyses, we had the exact same null model, which is all the way from up at line 195. And so again, that's the same thing that we said before. The null model only needs to be calculated one time as long as you're focused on the same outcome and set of covariates. So we're going to move on now, still focusing in on scat, and we're going to demonstrate how to read in Plink data and also conduct analysis when you have Plink file formats. So Plink is by far the most popular software for genome-wide association analysis. A lot of the data file formats are still commonly used also for rare variant and sequencing data. And there's also a Plink-seq. And so one of the nice things about scat is that it can actually directly read in and process Plink file formats. So what we're going to do then is we're going to first look at just a few examples that are inside of the virtual machine. So the first set of steps is we need to define a whole bunch of different files. So we're going to define a bed file, a BIM file, a FAM file, a set ID file, an SSD file, and an info file. So the bed, the BIM, the FAM, these are all standard things that you would have in any Plink analysis. All right, so the bed, the BIM, and the FAM. The set ID is a file that you need to prepare. And so just to see what is inside of the set ID file, here's an example. Well, let's go into the lab examples folder. We're going to pull up the particular Plink example folder and pull up the set IDs. And so this is an example set ID file. What you have is an identifier for the set. So in this case, we're going to call it gene1. And then this is an identifier for the SNP, in this case called SNP0056. For real data, this could be an RS number or an Illumina identifier or something. It's just a unique identifier for the SNP. And so line 1 is saying that SNP0056 is mapped to gene1. Line 2 is saying that SNP0083 is mapped to gene1, and so on and so forth. And so, again, you have the set identifier followed by the particular SNP identifier. And so if you keep going, then now these variants are mapped to gene2. And if we scroll all the way down, in this case, this SNP is in gene5. All the way down to the bottom, we have variants that sit inside of gene10. All right, so the identifier here, it doesn't have to be called gene 1, 2, 3. It can be whatever gene name you want or whatever region identifier. You can call it anything. You can call it Bob. It doesn't matter. And then these guys have to be the SNP IDs somehow. This is a file that you have to create. It is probably one of the more irritating files to create, but it is something that you need to specify a priori. SNPs can belong to multiple sets. That's not a problem, and duplicates are automatically filtered out later, but in general should be avoided. So it's just a file here. The set ID is something that you need to provide, which maps snips to particular set ID sets. So that's a set ID file. The SSD file and the ssd.info file, these are files which are going to be created inside of the analysis and are things that you don't need to worry about creating. This is going to be the file name. But you don't actually need to create these by yourself. So we're going to run lines 232 through 237 where we define the file names. And then we're going to generate the SSD file from the set ID files and we'll generate the SSD files. So if you have a binary PED file, you have to generate the SSD file first. If you already have an existing SSD file for this data set, then you don't need to run it again. So again, this is a line which can sometimes be very, very slow, but which only needs to be run a single time. So if you have a particular data set, this only needs to be run one time for a given set of variants and a given set of snip to set mappings. So we highlight this and we hit run. And then you see down here, it check for duplicate snips in each snip set. There are no duplicates in this case. There's 1,000 samples, so 1,000 individuals, and there's 10 sets, which is to say 10 sets of variants that we want to analyze. We do that. There's gene 1 through gene 10. And then there's 984 total SNPs, and it tells you that the SSD and info files have been created. Now we're going to read in the phenotype information. So fam is read underscore plink underscore fam. It's not a binary. And so we highlight lines 245 through 246, hit run. And now Y is now read in. If you look at what Y looks like, it's again just a quantitative trait in this case. Then we're going to open up the SSD file. So ssd.info equals open SSD. If you have another one that's open, it'll automatically close it. And so it tells you there's 1,000 samples, 10 sets, so 10 genes, and 984 individual variants in there. Lines 253 and 256 are just giving you a little bit more, are just giving you exactly that same information. Then to actually run the analysis, what we're going to do is, again, you specify the null model. So Y just depends on an intercept. It's, again, a continuous trait. All right. And so we store that, we run that, and store that inside of the object. And then now to run scat across all of these sets, we do scat.ssd.all. All right. ssd.info. So that's the SSD file that we opened, and we give it the object, which is the null model. So let's highlight that and hit run. All right. So it gives you a warning. There was missing data inside of this particular, inside of the variance inside of this particular example, and it applied imputation. So the imputation that it applies is not a smart imputation. It simply is imputing based off of Hardy-Weinberg equilibrium. So if you have a lot of missingness and if that's really a concern, then you should probably run something like mock a priori. All right, so then to actually see the results, we can just do re.scat. So that's also on line 259. We hit enter, and so it has a number of different components over here. The one that you really care about is $results. So we can actually do this. Look at re.scat $results. And this is the results table. The first column over here gives you the set identifier. So in this case, gene 1 through gene 10. It could also be a gene name, whatever. And then this is the p-value for the association between the variants inside of this particular gene and the outcome using scat. So this is the p-value for gene 1, gene 2, all the way up to gene 10. This is the number of markers that are inside of gene 1, gene 2, and gene 3, all the way up to gene 10. And then this is the number of markers that are actually used inside of the test. In this case, they match up perfectly, but in real data, it may not correspond exactly due to certain things like non-polymorphic variants or some sort of QC filtering that is done inside of SCAT. So if there's a lot of missingness, for example. All right, but it's very, very easy to run scat, again, with Plink data. You simply need to specify all of the files. It takes a little bit of effort. The hardest part in this case is setting up the set ID file. I'm happy to provide code for that if you are interested. With just a few lines, you've analyzed the association between each of these genes and the outcome. So here we've done 10 genes at a time. We can do the same thing with scat-o. The code is very, very similar to what you would run for scat, except now we do scat.ssd.all. You feed in the ssd.info, the null model, which again has not changed, and you say method equals optimal.adjusted. And so if we highlight 268 through 269 and hit run, you get a p-value for the association between each of the variants and the outcome using scat-o. All right, so this is the p-value from scat-o, associating the variants inside of gene 1 with the outcome, all the way up to gene 10 with the outcome. Again, the other columns are as before. So we can run scat in this way, but it ends up that you can also trick the software into doing burden-based testing. So recall that your weighted count-based collapsing, it's just the omnibus version of scat with a row set equal to 1. So if you want to do burden-based testing with Plink files, you can also use the scat software. So we do the same thing as before, except now we specify that r.core equals to 1. So the syntax is very, very similar to what you would have typed if you had run scat by itself. Type this in, we hit run. And now what you end up with is the set ID, and then this is now the burden-based p-value for the association between the particular variants inside of this gene and the outcome, one at a time. So this is just the burden-based test. So now what we're going to do is we're going to basically repeat this analysis, except we're going to use some more realistic data. So this is from chromosome 22, and we're going to look at a phenotype Y1. In this case, it's artificially constructed, but it illustrates what's going on when you have more genes and you also have identifiers that are a little bit more realistic. The how to get all of these files generated should also be on the virtual machine. It's inside of the folder chromosome 22 input files and code. It's a little bit burdensome to run, and so I've already provided all of these files for you. The code and how to generate all of these is also available to you. So the first thing, again, that we're going to do in running this is we're going to define all of the file names. So we have the bed, the bim, the fam. The co file is a covariate file that we're going to specify. And then the set ID file is something that you needed to construct. In this case, I provided the code for constructing this. If you see what it looks like, again, what you have is a whole list of gene identifiers and the corresponding SNP identifier. So all of these SNPs live inside of the A4 GAL gene. And then if you go down, again, these SNPs live inside of a different gene, and so on and so forth. So let's go back to our code. So we're going to run lines 286 through 292. And so we highlight those, hit run. And so we've just defined all of the file names. Then we're going to have to generate our SSD file, all right, because we're dealing with binary Plink files. So we hit this. And what happens is it says, oh, it created the file. So it checked for duplicate SNPs in each SNP set. There are no duplicates. There's 192 samples, which is say individuals. There's almost 400 sets, so 400 different genes, and about 10,000 SNPs in total that are mapped to these genes for analysis. Next up, we're going to read in the fam file. So we run this. And so all of that works. We're going to get a null model. So the object equals scat underscore null underscore model. So the outcome is y.1. There's two covariates, x1 and x2 inside of the data fam. And the outcome type is again continuous. So we highlight lines 302 and 303 and we hit run. Okay. And this is our null model. We're going to have to open up the SSD file again. All right, and if you hit run, you'll note that it first closed the previous SSD file that we had left open. It's good practice to close. In this case, I did not, to show just that it automatically closes it. And then here, it again tells you 192 samples, 399 sets, and 10,000 different variants to analyze. All right, and so 312 and 315 lines are just basically reiterating this information. First, we're going to run scat. So again, we're going to set that into rh.scat. And so we're going to do scat.ssd.all. You specify the ssd.info and you put in the null model. So if you hit run, it takes a second to run, but you can see very quickly it finishes. So there are a few warnings. Let's just see what they are in this case. And it's simply that it's telling you that there's a number of SNPs that have high missing rates or are non-variable, which is say non-polymorphic. But if we look at what re.scat looks like, What it is inside of the results file is, again, the same thing as what we had before. It's a giant matrix where a giant table where the first item is the gene name. The next thing is the p-value for the association between the variants inside of this gene and the phenotype. N.marker.all, again, this is the total number of markers of unique markers that fall inside of this gene. N.markers.test, this is the number of markers that were actually used in the association analysis. And in this case, it does not necessarily match up with the total number of markers because, as we saw before, there's some variants that have a lot of missing or no variation that are non-polymorphic, and so those are automatically dropped. So these two numbers do not always match up, but knowing this can be useful. But with that being said, you've been able to assess the association between 400 different genes and your outcome very, very quickly. It takes a little bit of work to set it up, but once you've set it up, it's very, very easy to use and runs pretty quickly. The next step is we're going to repeat this doing a burden-based test by tricking the scat function into running a burden-based test. We simply set r.core equal to 1. So if we hit run over here, again, it's pretty fast, and with that, you have re.burden. And so let's see what that is, what's inside of there. And it's, again, just a giant, if you look at the results component, it's, again, just a giant table that has gene name, all right, p-value for association between the variants inside of this and your outcome, and the number of markers used should be the same as before. The scat software can be used very, very quickly to actually do the association analysis. I'm not going to run line 322. You can run that on your own machines at home, simply because once you set method equal optimal.adjusted, it takes a much longer time to run. Okay, with that, I will stop here. If there are any questions, please do feel free to email me.